In this video, we're starting section 6.3 on permutations and combinations. Our goals are to count the number of ways in which we can select some objects from a larger group when the order matters, that's called a permutation, and when the order doesn't matter, and that's called a combination. And then we'll talk about how we can recognize when we use permutations versus when we use combinations versus when we use our other counting methods that we've seen already. All right, so in this video, we will focus on what permutations are. And I want to motivate this through some examples. So the first example says there are 5 runners in a race. Assuming there are no ties, in how many orders can they finish? Okay, so I know that there's 5 runners, so there's going to be 5 spots in which they finish. So let me just draw 5 spots here. So let's focus on this first place finisher first. Well, there would be 5 choices for that first place. It could be any one of these 5 runners. So I'm going to write a 5 up there. And then once I pick whoever's in first, well, that still leaves me with 4 choices. 4 choices for who I could pick for second place. So I'm going to write a 4 up there. And once I've picked the first 2 finishers, then there's still 3 choices for who could be third. And then there'd still be 2 choices for who could be fourth. And once I've picked the first 4, well, that leaves me with just 1 choice for who would be in that last spot. Okay, so we've seen before that when we do something like this, we're picking the number of choices we have for each one of these spots. To get the total, we multiply these together. So 5 times 4 times 3 times 2 times 1. And if I multiply those values together, we get 120. 120 possible orders. One of the ways I can multiply those kind of quickly is to notice that, 5 times 2 would be 10. 4 times 3 would be 12. So 12 times 10 is 120. And then multiplying by 1 doesn't affect that. I might also notice that, 5 times 4 times 3 all the way down until 1, we've seen special notation from this before, maybe in earlier math classes. This is what's called 5 factorial, where we represent the factorial with this exclamation point. So let's do a brief review of factorial. So remember that n factorial is just the product of all the positive integers starting at 1 up until when we reach n. So this was 5 factorial up here. So what we've seen in this example is this factorial it means something in terms of counting. It's the number of ways in which we can arrange n distinct objects in a row. So 5 factorial was the number of ways we can arrange 5 objects, these 5 runners in a row, and determine their placings. So one question is, well, what would 0 factorial be then? So 0 factorial would be the number of ways in which we could arrange 0 objects. But if there's 0 objects, what can I do? There's just one thing that I can do, which is to do nothing. Do nothing. So there's one way to do that, which is to just do nothing. So 0 factorial should just be 1, according to this counting interpretation. So this might not be entirely satisfying, especially if it's the first time you've seen it. So let me give another reason for why we'd expect 0 factorial to be 1. So I'm going to write this on the side here. So let's write down a few factorials. So I'm going to think about what 0 factorial should be. I know 1 factorial would just be 1. 2 factorial is 1 times 2, which is 2. 3 factorial would be 1 times 2 times 3, which is 6. And I'm going to notice some patterns here. To get from 1 factorial to 2 factorial, we multiply by 2. From 2 to 3 factorial, we would multiply by 3. So then going down in the other direction, to get from 3 factorial to 2 factorial, we would divide by 3. To get from 2 factorial to 1 factorial, we would divide by 2. So then to get from 1 factorial to 0 factorial, if this pattern continues, I should be dividing by 1. But if I do 1 divided by 1, that's just 1. Okay, so this is another way I can see why 0 factorial, why we should define it to be 1, so that it makes sense according to the patterns that we see with factorials. All right, so let's do another example. So in this next example, it says, I have 11 books and want to keep one in my office, one on my bookshelf, and one by my bed. And how many ways can I do this? So for this problem, we are thinking about, there's 3 books we're picking. So I'll write a slot for each one slot for each one. So maybe the first slot represents which one goes in the office. The second one might be which one goes on the shelf. And the third one is which one goes by my bed. So if I think about the one in the office first, well, there's 11 things I could choose from for that spot. Once I've picked the one in the office, there's still 10 remaining for the shelf. Once we've picked those 2, there's still 9 remaining for what could go by my bed. So then, of course, I multiply these together. And then 11 times 9 is 99. Multiplying that by 10, I get 990. So there's 990 ways to do this. So these quick examples are examples of what's called a permutation. So we're ready for the technical definition now, which says that a k permutation on a set of n objects, where n is greater than or equal to k, is a selection of k objects from the set of n. So in other words, we are picking k objects from a set of n objects. And the order in which we pick the objects matters. And that was the case in these examples. Because in the first spot, that was denoting my office here. In the second spot, that was denoting my shelf. In the third spot, that was denoting which one went by my bed. So whichever book I put in this first spot was going to go in my office versus whichever one went in the third spot would go by my bed. The order in which we assigned a book to each one of these spots mattered. Similarly, in this first example, the order in which we picked a runner for this spot versus picked a runner for this spot mattered, because that would determine their position in the race. We'll see examples in a future video where the order in which we pick the objects doesn't matter, but for right now in these examples, it does. So we can represent the number of permutations of k objects from the larger set of n objects. We denote that with a capital P for permutation, and then parentheses we're at n comma k. So let's get a formula for P of n comma k for these number of permutations. So I'm going to think about, well, how many choices do I have for that first spot, and then the second spot, the third spot, dot, 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 up until the last spot. Well, there's n total objects I'm picking from, so that means there's n choices for that first spot. So I will write n up there. Once we pick what goes in that first spot, well, there's still n minus 1 choices for that second spot, n minus 1 choices for that second spot. So let's write n minus 1 there. And once I do that, I start to see a pattern. Now there's n minus 2 choices for this third spot. So, how many choices are we going to have for that last spot? I'm going to leave myself some space here. I'm going to put a blank. So how many choices are there going to be for, this is the kth spot? So it might be very tempting to say, well, isn't it just, oh, and I realize I never wrote n minus 2 up here. Let's go ahead and do that. So n minus 2. It might be really tempting to say, well, isn't it just n minus k? But not quite. So one of the ways I can see why is I noticed that, like, for the third spot, it wasn't n minus 3, it was n minus 2. And for the second spot, it was n minus 1. And even for the first spot, it wasn't n minus 1, it was just n. So one thing I might notice is n is actually the same thing as n minus 0. So when I think about this number that I'm subtracting, I'm actually starting this counting at 0, and then 1, and then 2. So by the time I get to the kth spot, what it should be is n minus, in parentheses, not k, but k minus 1. Because if I'm starting the counting at 0, and then I reach k minus 1, I've actually counted k different integers. Okay, so let's go ahead and write that up top as well. N minus, in parentheses, k minus 1. And if I wanted to simplify this by distributing the negative, I could. This is n minus k plus 1. So we multiply these together. Multiply, 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 and multiply. All right, so this gives me the general formula. So let's write this on the next page. The number of permutations of k objects from a set of n objects is n times n minus 1 times n minus 2, dot, 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 up until n, let me just go ahead and write it in this distributed form, n minus k plus 1. It ends up being this. All right, so I'm going to highlight this. We get this formula for the number of permutations. There's another very common way that this is expressed. So I want to end the video by just briefly talking about that. So let's do some algebra to re-express this. So I got n times n minus 1 times n minus 2, dot, 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 n minus k plus 1. So one thing that I notice is this kind of looks like the starting of a factorial, but it doesn't have all the terms that I need at the end to be a factorial, because I would keep needing terms until it like dropped down to 1. So let's try to get it to look like that. So what I would still need is I would need to then multiply by the next thing smaller, next integer smaller than this, which would be n minus k. And then one smaller than that is n minus k minus 1. And if I keep going, eventually I'll get times 2 and times 1. So if I decide to multiply this on top, I also have to multiply by that on the bottom. So let's also multiply by n minus k times n minus k minus 1, dot, 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 up until 2 times 1 on the bottom. And now my numerator is a factorial. Now it's n factorial. And the denominator actually also is a factorial. It has all the integers from 1 up until n minus k. So the denominator would be n minus k, in parentheses, factorial. So I'm going to highlight this as well. This is another way we can express this formula for the number of permutations. Typically, when I work through examples where I'm just making a small number of choices, like here I was just picking 3 things, I don't end up using the factorial. I could if I really wanted to. I just think it feels like overkill a little bit, because I could just more quickly do it like this, just using this product of things by thinking about it just kind of conceptually. But, if I was picking a larger number of things, like if I was picking 30 things from a set of 50, then it's really tedious to write it out like this. And then the factorial form would be more efficient. All right, so there we have permutations. In the next video, we will talk about something called a combination. And that refers to when we're picking objects, and the order in which we pick them does not matter. So we'll talk about how that's a little different.